Free radical halogenation is normally not a good way to produce something because it's very inefficient. The radicals are so incredibly reactive, they normally react to the very first thing they come into contact with. But, as we'll see, there are some ways we can take advantage of this and still be able to get something that we're planning on getting. And even more interestingly, there are going to be other reactions that are very, very highly selective, even though they are free radical reactions. So the first one is a typical example of how one of these reactions would take place. Chlorine reacting with propane. And the products are a whole variety. 1-chloropropane, 2-chloropropane, 1,2-dichloropropane, 1,1-dichloropropane, and the list continues to go on. So if we're looking for just one of these things, it's not a very good way of getting one. We can get it, but it's very inefficient, and then of course after we'll have to separate it. But on some industrial scales, all of these might have use for something. So in those kinds of cases, it may not be important. But if selectivity is an important factor in the reaction we're trying to do, then we need to look somewhere else. So here are two examples of higher yield free radical reactions. The first one, it's obvious what's taking place. We're looking for chlorocyclohexane. And the reason it has a higher yield is because no matter where this chlorine hits, it's going to be the same. If it goes to the top hydrogen or the lower hydrogen on any of these carbons, it will be the same. So as long as it only hits that ring one time, we will get exactly what we're looking for. The second example is a lot more interesting. We have a carbon with many branches, but if we notice, the yield is 90%, which is very, very high, especially for a free radical reaction. So what causes this yield to be so high and these other ones to be so poor? With free radical reactions, what we're going to be looking for is a way to take advantage of its indiscriminate reaction, it's indiscriminate reactions, like in this example here, where it doesn't really matter where it reacts with, we're going to get the product we want anyways. Or we're going to have to look for a mechanism by which there is a weak hydrogen, and that is what this is right here. It can be a weak hydrogen or some other weak group that is more reactive than the other ones, which will cause it to be preferred over the other hydrogens or groups. So we'll have a look at why this is happening. And it has to do with the stability of this carbon right here. When a bromine radical reacts with this hydrogen is easier to remove, because when this radical forms here, it's going to be more stabilized. So hypothetically, let's just say it just selected any hydrogen here. It could take this one right away, the one less energy, or it could take one of these ones. If it takes one of the outside ones, what is going to happen is that this radical will shift onto the middle carbon, because when there is a carbon radical, the carbon radical is going to draw electrons from the other atoms around it, from these hydrogens and this carbon to itself. When the carbon is here, it's not able to get as much electron density as it would if it were here. When it's here, it can draw electrons from this carbon, and this carbon. So it's more stable. And this is what this shows. This hydrogen, if it were to react with this outside hydrogen out here, this hydrogen would shift over and shift the radical to the more stable position. So either way, no matter where this bromine reacts, it's going to get most of the time this carbon radical. This step is very fast. This carbon radical is incredibly reactive, and it's going to shift immediately. And then when the bromine comes along, it's just going to take the place of the hydrogen and then create another bromine radical and continue the chain reaction. Another example of a weak hydrogen is in this alkene. Here, the hydrogens in these positions next to the double bond are more reactive than the hydrogens that would be over here. And it's for the exact same reasons. When one of these hydrogens gets removed, it's able to borrow electron density from this double bond. This is a flat bond. And then when this gets taken, it will also become flat as well. So it will be able to move along the ring. Which we can see this reaction has an 80% yield, which is very high as well. So we'll look and see what happens. Bromine radical comes along, takes one of these hydrogens, and it doesn't matter which one of these gets taken, the same thing will occur. There will be a resonance structure stability where the radical will be able to borrow electron density from this double bond, which has high electron density. And this is, it's not one or the other, it's something in between. This is just the best way to illustrate it. It's not here and then here shifting back and forth. It's just one smooth thing, but this is the way it's illustrated. So think of these two things as one. So it becomes more stabilized in these positions, and as a result, when the bromine comes in again, it doesn't matter which end it reacts at, it will give us the same molecule. So when dealing with free radical halogenation, we have to understand that these things are very, very reactive, and we're going to have to look for a situation where we can use the very reactive nature of it to our advantage and have a situation where most of the product we're going to get is something we want anyways, like in this reaction. We're not really doing anything special here, it's just we're taking advantage of the fact that as long as only one chlorine hits, then we're going to have something we want. That's why when dealing with free radical halogenation, we want to use very little of the halogen. We don't really need to add much because a new radical is produced, it's self-sustaining. So if we use a very small amount of halogen, then we can make sure that we have the maximum yield of product. So we don't get it reacting multiple times, because the probability will be high that it will hit one of these new ones rather than one of these ones that's already been reacted. And then the second example, of course, is taking advantage of the fact that in some molecules there will be a way for a carbon radical to be formed in a very specific location most of the time, because it will be able to get stability from molecules surrounding it, whether from donating of these sp3 bonds, like in this example, or getting electron donations from a double bond sp2 hybridized.